Hello students. In the last lecture, I discussed about the inventory models with deterministic demand. First, I classified the inventory models on the basis of demand rate and replenishment rate. On the basis of demand rate and replenishment rate, we have three types of model here. The model one are having demand rate uniform and replenishment rate infinite, and the models of second type are having demand rate non-uniform and replenishment rate infinite, and model third are of type having demand rate uniform and replenishment rate finite. In the previous video, I discussed about the first model, that is the model with demand rate uniform and replenishment rate infinite. Today in this video, I am going to discuss about the model second and model third, that is the models with demand rate non-uniform and replenishment rate infinite, and the model three are of the types demand rate uniform and replenishment rate finite. Let's start discussion one by one. The first we discussed about the second type of models having demand rate non-uniform and replenishment rate infinite. In this model, all assumptions are same as we discussed in model 1, with the exception that instead of uniform demand rate capital R, we are given some total demand capital D to be satisfied during some long time period capital T. Thus, demand rates are different in different order cycles. Thus, demand rates are different in different order cycles. Let Q be the fixed order quantity each time the order is placed. Then the number of orders are given by capital N is equal to capital D over Q. Capital N represents the number of orders, where capital D is the total demand, and Q be the fixed quantity order each time the order is placed. The graphical picture of this type of model is given as this is the graphical explanation of this type of models, that T1, T2, T3, T4, Tn are the time intervals, and capital T is the total time. T1 is the time interval between order 1 and 2. T2 is the time interval between order 2 and 3, and so on. And the capital T is the total time. And Q is the fixed quantity ordered each time the order is placed. Then the total time capital T is given by T1 plus T2 plus so on up to Tn. Now the holding cost for the time period capital T will be this holding cost I earlier calculated in the discussion of model 1, that is the holding cost is given by half QT into C1. If time interval is T1, then holding cost is half Q T1 into C1. If time interval is T2, then holding cost is half Q T2 into C2. C1. As the holding cost is same, therefore it is C1. Now, if the time interval is T3, then the holding cost is half Q T3 into C1. The total holding cost for time period capital T will be uh, sum of these all holding costs during two different time intervals. That is half Q T1 C1 plus half Q T2 C1 plus so on half Q Tn into C1. Half Q C1 is taken out from the brackets. This T1 plus T2 plus so on up to Tn becomes the total time T. Therefore, the holding cost for time period capital T will be half Q C1 into capital T. After that, the ordering cost will be, what is the ordering cost? Ordering cost will be C3 into number of orders, C3 into capital N. This is basically C3 into number of orders, and N is basically, we have already explained N, that number of orders is equal to total demand upon quantity ordered each time the order is placed. This replace N by D by Q, then the total ordering cost will be C3 D upon Q. Now the total cost equation for fixed order size Q will be, this is given by half Q C1 into T, that is total holding cost, and the total ordering cost, that is half Q C1 into T plus C3 D upon Q. Now for minimum cost, we have to put its first derivative equal to 0, and simultaneously its second derivative should be positive. Now it's after calculation, its first derivative is, this is its first derivative, that is half C1 capital T minus C3 D upon Q square. Put it, equate it equal to 0. After equating it to 0, we will get Q as square root 2 capital C3 capital D upon capital T upon C1. And for this value, second derivative is always positive for this value of Q as given above. Therefore, the optimal load size is given by this formula. This is the formula for optimal lot size. Further, the minimum total cost is given by, put the value of Q in this equation. Put the value of Q, that is the value of optimal size, in this equation. After putting the value of Q, we will get the minimum total cost as square root 2 C1 C3 capital D upon capital T. Also, we find that results for this model can be obtained if the uniform demand rate capital R in model 1 is replaced by average demand rate capital D by capital T. Now, in the classical economic order quantity model, the replenishment rate was assumed to be infinite. The entire quantity ordered was delivered in a single lot. This is possible only for bought out atoms and is simply unthinkable for maiden items. Therefore, we have now model of third types, that is the models with demand rate uniform and replenishment rate infinite. Replenishment rate finite. I am not going into derivation of this type of model. After the derivation part, we will get its total average cost per unit time by this formula, that is half capital K minus capital R upon capital K into capital C1 into Q plus C3 capital R upon Q. And after derivation, optimal load size is given by this formula, optimal time interval is given by this formula, and optimum average cost per unit time is given by this formula. Now, this various symbol has various meanings. Capital R represents the number of items required per unit time. Capital K represents the number of items produced per unit time. C1 is the holding cost. C3 is the cost of setting up a production run. And Q is number of items produced per run. And Q is equal to capital R into T, where T is the time interval between runs. Also, the formula for maximum inventory is given by this. This is the formula for maximum inventory in terms of quantity, and this is the formula for maximum inventory available at the end of time t1. Now, there are particular cases of model 3, that is, if we put k equal to capital R, then C naught becomes 0, which means that there will be no holding cost and no setup cost. And if we take k as infinity, that is, production rate is infinite, this model reduces to model 1, which I have already discussed. Now, based on these two models, let's discuss some examples. The first example is a company has a demand rate. A company has a demand of 12,000 units per year for an item, and it can produce 2,000 such items per month. The cost of one setup is rupees 400, and the holding cost per unit per month is rupees 0.15. Find the optimum load size and the total cost per year, assuming the cost of one unit as rupees 4. Also find the maximum inventory, manufacturing time, and total time. Now, demand rate for company is 12,000 units per year for an item. That is, capital R is given as 12,000 units per year. Also, it can produce 2,000 such items per month. That means production rate is 2,000 items per month. If we convert into yearly, then it becomes 2,000 into 12, that is 24,000 units per year. Also, the cost of one setup is rupees 400, that is, C3 is given as rupees 400 per setup. Holding cost per unit per month is rupees 0.15. If we convert it into yearly, then it becomes rupees 0.15 into 12, that is rupees 1.80 per unit per year. Now, the optimal, we have to calculate optimum load size. Already we discussed about the model 3, and the formulas for optimal size, for manufacturing time, for maximum inventory is already given. The formula for optimal load size is q naught as square root of capital K upon K minus R, square root of 2 times C3R upon C1. Every coefficient, value of every coefficient is given. The value of k is 24,000, value of capital R is 12,000, value of C3 is 400, value of C1 is 1.8. After putting all the values, we will get optimal load size as 3 to 6 units per setup. And now we have to calculate total cost per year. As we have there is demand of 12,000 units per year, and the cost of one unit is rupees 4. Therefore, total cost is 48,000, that is 12,000 into 4 plus square root of 2 C1 C3 R, square root of k minus R upon k. Putting all the values, we get total cost as 50,940 per year. Also, we have to find the maximum inventory, then manufacturing time, then total time. The formula for maximum inventory is K minus R upon K into Q naught. We have already calculated optimal load size. Put the values here, and after putting the values, we get maximum inventory as 1632 units, and the max manufacturing time is given by maximum inventory upon K minus R. Again, putting all the values, we get manufacturing time as 0.136 years. Total time is given by optimal load size upon capital R. Already we have calculated optimal load size. This is 3264 upon 12,000. Then the total time is 0.272 years. The next example is an item is produced at the rate of 50 items per day The demand occurs at the rate of 25 items per day. If the setup cost is rupees 100 per setup and the holding cost is rupees 0.01 per unit of item per day, find the economic load size for one run. Assuming that shortages are not permitted, also find the time of cycle and minimum total cost for one run. An item is produced at the rate of 50 items per day. That means production rate is 50 items per day. Therefore, capital K is 50 items per day. The demands occurs at the rate of 25 items per day. Therefore, demand rate is capital R is 25 items per day. If the setup cost is rupees 100 per setup, that means C3 is given as rupees 100 per setup and the holding cost is rupees 0.01 per unit of item per day. That means C1 is rupees 0.01 per unit per day. Now we have to calculate economic load size, optimal load size. Optimal load size is given by this formula. After putting all the values, the optimal lot size is 1000 items. Also we have to calculate time time of the cycle. The time is given by Q naught upon R. We have already calculated Q naught. We can simply put the value of Q naught and then take the value of capital R. We get uh, total time as 40 days. Also, we have to calculate minimum daily cost. The formula for minimum daily cost is this. And after putting all the values, we get the minimum daily cost as rupees 5. The minimum daily cost as rupees 5. Now, the minimum total cost per run is the minimum total cost per run is we have we have minimum total cost per run is minimum daily cost is rupees 5 and we have time of cycle 40 days. Therefore minimum total cost per run is 40 into 5, that is 200 rupees total cost per run. In the next video, I I I discuss the you can do some more example on the basis of model 2 and model 3. In the next video, I am going to discuss about the inventory models with probabilistic demand. Till then, thank you so much.